Hello all, uh, welcome to my course on methods of adhesion measurement, theory and practice. We are at lecture 43 today and we are discussing about a sandwich layer of elastic adhesive between two parallel plates. And here are the references, and this is the geometry that we are discussing, in which there is this elastic film which is bonded to this rigid substrate and it is being pressed or being pulled off from the top by a rigid plate which is in contact. And we discussed this problem in the last 3 lectures, in which we derived these expressions for an compressible elastic film and for an incompressible elastic film. Okay. This is the compressive load applied per unit width of the plate. Here this delta is the deformation from the top surface of the film. So, these are the expressions that we got. So, today we will continue to discuss the problem that we are discussing in the last lecture. So, remember here we have this film of this given dimensions and we have carried out two kinds of experiments. In one case it was sheared from the top, from there we obtained the shear modulus of this film to be 0.5 megapascal, and then we have done the second experiment in which we have compressed without shear, and in that case we have the data of compressive load as a function of this delta, the deformation that we have. So, here using this shear modulus, okay, we can actually obtain the Poisson ratio. That is the idea, that is what I would like to do. So, here let us say that the compressive load is related to the delta z, that by this particular expression. Here you see we know all the terms, all the values except this Poisson ratio here. So, here let us first plot this f j as a function of delta z from this particular data. Data is given in terms of kg here, kilogram here, it should be kilogram, kg here, kg here, and so there we have to multiply it by the acceleration due to gravity to make it Newton. So, that is what we have done here, and then now we can plot this f z as a function of delta z. Plot looks like this, and we can have this base fit and find out this particular slope. So, slope gives basically the spring constant. So, that is equal to 4 into 1 minus sigma square by 3 h by L whole cube into mu into this w over here. So, this whole thing that will be equal to slope here. So, the slope comes out to be 27 x. So, let me write here 27, and this is in Newton micron. So, it should be 10 to the power 6. Remember that this is in micron here and this is Newton here. So, this should be K has a unit of Newton per meter, right. So, therefore, it should be like this. And so, now let us write 1 minus sigma square. So, this will be equal to 3 by 4 okay, into h by L whole cube and 1 upon mu omega into 27 into 10 to the power 6. Let us put the values. So, this is 3 by 4 and this is h is 1.5 millimeter. 1.5 into 10 to the power minus 3 divided by L is 15 millimeter. I will always use this SI units, 1 by 0.5 megapascal 10 to the power 6 into W is 50 millimeter, 50 into 10 to the power minus 3, and in the numerator this is 27 into 10 to the power 6 over here. So, like that, and now you have to use your calculator to obtain whatever is the values. Please do that. I have done that, and this comes out to be 0.81, and from there by this sigma, that is the Poisson ratio, comes out to be 0.436. So, by using these two kinds of experiments one can actually get these results. So, that is the way it is. So, now what I will do is, so far we were compressing this top plate on this particular elastic film bonded to this bottom plate, and this is from the top plate we are compressing it. Now, what we will do, we will think that there is adhesion at this particular interface. So, between this film and the top substrate, okay, there is this adhesion, and so we would like to know that in presence of some kind of adhesion, that is work of adhesion WA, okay, what is the force, pull of force that needs to be applied to separate it. So that is what we like to do now. So remember, work of adhesion is given over what? This is gamma 1 plus gamma 2 minus gamma 1 2. So this is the surface energy of surface 1, let us say this is the film, and then this is gamma 2, that is let us say the substrate, that means this top substrate, minus gamma 1 2. So this is the work of adhesion. So what it means is that when this the top plate comes in contact with this particular substrate, there is a amount of energy that gets lost, because the interfacial energy will be smaller, okay, than these quantities. So WA is equally positive, work of adhesion is positive. You need to apply some amount of energy in order to separate it, okay, remember that. So when this plate, top substrate comes in contact with this film, the surface energy that decreases, okay, that is the way it is. So now in order to obtain this load, okay, we need to consider the total energy of this system. So total energy will be U elastic energy by U mechanical energy and U surface energy. So elastic energy will be equal to what? So that we have already derived the expression, that is this expression. So this expression F is equal to 4 into 1 minus sigma square blah blah, and now we integrate it. So that is F into d delta 0 to delta. So the delta is the pull of distance, remember that. So now that we are pulling it, so the delta is actually the pull of distance. Let me write it for you. This is pull of distance. So this kind of treatment we have done it earlier in this particular course. So it is not new to you, but nevertheless for the sake of completion I will complete it the whole thing. So 4 into 1 minus sigma square by 3 h cube L cube mu W, and then delta will be, here it will be delta square by 2. So this is actually the elastic energy of this particular film. So this much amount of energy gets stored, okay, when the film is subjected to this load F and it displaces by amount delta. Now what is the surface energy? Equal to minus of work of adhesion, okay, into the area. So the area is L into W. And then what is the mechanical energy? So mechanical energy means that the external load has done some work, so it has done some, so it is actually minus F into delta by 2. So 0 to delta has been deformation. So this is the amount of energy that it has spent. So the total energy, okay, total energy is UT, that is equal to U elastic plus U mechanical energy plus U surface energy. So this is equal to, this is let us say 2 by 3 1 minus sigma square and h cube, this is L cube, this is mu and W, and this is delta square here, and then delta square. So 2 1 minus sigma square by 3 h cube L cube mu W and delta square, this is elastic part, minus this is F into delta by 2 and minus this is WA into L into omega, that is the width. So this is the total energy of this particular film, and see here L is a parameter, the length spatial dimension of the parameter. So we need to minimize this energy, we need to see that what is the minimum amount of energy that needs to be applied, okay, with respect to L. So therefore del UT by del L, we have to write it equal to 0. Minimum of the energy with respect to L, that needs to be found out, and so therefore del UT by del L equal to 0, and that leads to, this is leads to over here 2 by 3 1 minus sigma square, this is h cube L cube, so 3 L square, and this is mu W delta square, and minus this is W A, and this small w is basically the width, this is equal to 0. So this I will first get cancel it, and this is 3 gets cancelled over here, and then finally I have delta, okay, that will be equal to WA into h cube, WA into h cube, 2 into 1 minus sigma square into mu and square root, L also has to be there. So, L square and this is square root, I hope I have done it right. So, WA into H cube, this is 2 into 1 minus sigma square and L square in the denominator and mu also denominator and the square root. So, this should be the expression for the delta. Okay. So, this is the critical distance at which this separation should occur, and the critical force also then can be calculated. Okay. Now, so therefore, let us substitute the expression for delta into the expression for F over here, and that will give me the critical load that needs to be applied. So, it is 4 into 1 minus sigma square 3 H cube into L cube into W into mu, and delta is square root of W A H cube by 2 into 1 minus sigma square by mu into L square. So, this is the force, the critical force that needs to be applied. So, let us say I am interested in critical stress. So, force divided by this is L into W, that should be my critical stress. So, let us say represented by sigma c. So, that will be equal to, let us put everything inside, this is L. So, it is L I have written. So, it is L square here. So, it is L square. So, it is L square is L here. So, it should be L here I guess. So, here this is L. Okay. So, this is I will keep it at H here and this is L here and rest I will put it inside. So, this W already gotten. So, mu square. So, it is mu here, W A here, this H cube. Okay. So, H cube. So, now I have taken one H. So, another H square is there. So, H square will go inside. So, it is H to the power 4. So, it is H cube over there. So, it is H. This is correct. And then 1 minus sigma square goes inside. So, it is 1 minus sigma square, because there is 1 minus sigma square here, and this is 4 by 3. So, 16 by 9. So, it is 8 by 9. So, it is 8 by 9 over here. So, it is like this. So, 4 by 3 that goes inside, 16 by 9. So, divided by 2. So, once it goes to square root, it becomes 16 by 9 and divided by 2, that is 8 by 9, and this mu goes inside. So, it is mu square. So, it is mu in the denominator here, numerator mu square. So, mu square by mu. So, that will be mu here, and work of addition is already there, H cube is there. So, in the H cube I divide it. So, here outside this is 3 H cube. So, 1 H I keep, another H square is left, H square I take it inside this square root sign. So, H 4. So, H cube by H 4 is 1 upon H here. So, this sounds good, and you can check this, you can check the dimension whether it is alright or not, and I think it is alright. So, this is like this. So, sigma square, and this unit will be in the unit of Newton per meter square, by the way, remember that. So, here this is the expression that we can derive, and now if I write sigma is equal to half for incompressible material, okay, and then I can derive the corresponding expression for the incompressible material, right. So, for incompressible material, let us write it sigma to the power 1 by 2. So, it is 1 upon 4, this is 3 upon 4. So, finally 3 3 yeah. So, it is L by H, okay, into square root of 2 by 3 mu W A by H, that is what it gets. So, you see that with respect to the earlier results with elastic half space, there was no thickness coordinate there, okay. So, it was only in terms of mu, W and all that, and now you see we have got this thickness coordinate here, and it varies quite strongly with respect to the thickness of the film. So, that is the important thing here, that as W for given W and given mu, okay, this quantity this sigma c, that will depend, that is a strong function of the thickness, and it is actually thickness to the power 3 by 2 minus inverse. So, as thickness decreases, the sigma c, the critical load that will be required, okay, to separate it will actually increase. So, that is what it says, okay, but then everything, remember, we have considered that the film remains in complete contact with the top plate or the initially before it starts separate. When it separates, it completely separates. So, that is the way it is. So, remember that aspect. So, we summarize these results, therefore, now so far we had up to these results, but now we have these new results. So, critical pull up stress. So, expression for critical pull up stress for both incompressible material, incompressible elastic film and compressible elastic film we have obtained, okay. Now, in all these cases, remember that the film at the top plate remains in slipless contact. So, that means that if there is no slip contact, so that means if the top plate is sheared, this film will also get sheared to the same extent. I mean the top plate is given some deformation or displacement in the x direction, the film top surface also gets deformed like that. So, that is the no slip contact. So, here there is a small problem here. Rigid plate is brought in complete contact with less 0.5, Poisson ratio 2.96, 0.48, thickness 500 micron, bonded to a rigid substance and is then pulled up. So, we want to obtain the pull of load. Pull of load is found to be 300 kg. Obtain the work of adhesion at the interface, that is what needs to be found out. So, the pull of load expression we already have, that is sigma c is equal to L by H square root of, this is 8 by 9 1 minus sigma square, this is W A mu by H, okay, like that. So, this expression we already have and that is what we are going to use. Now, it is sigma c given and here the data is given in terms of 300 kg, that is the load given. So, we have to multiply it by the area. So, F will be equal to sigma c into L into W, this is the width. So, that will be equal to L square W by H, L into W to multiply. So, that is what I have done. So, 8 by 9 into 1 minus sigma square and W A into mu by H, that is the result. So, now let me put it. So, this is 300 kg means 3000 Newton, and this is L, length of this is 15, length of the lateral dimension of the film are 1.5 centimeter. So, 15 millimeter. So, 15 into 10 to the power minus 3 square into W is 50 centimeter. So, 50 millimeter, 500 millimeter. So, let us say this is 50 means 0.5 meter and thickness is 500 micron. So, 500 micron. So, 500 10 to the power minus 6 over here into square root of 8 by n. So, 8 by 9 here into 1 minus sigma square. So, that means 0.48, this is square, right, and W A is the thing that needs to be found out. Mu is given to be 2.96 megapascal, 2.96 into 10 to the power 6 and film thickness H is again 500 into 10 to the power minus 6. So, this is the way and needs to be found out. So, I think we can find it out, it is not so difficult, just needs to do little bit of calculations in the calculator and we can find out work of addition. So, we have done all that. So, I have written actually better way, nicer way over here, which is good. And then finally, we have this expression to be W, okay, is equal to 0.044 Newton meter per meter square, joule per meter square. So, that is 44 millijoule per meter square. So, the work of addition, okay, after putting all the numbers and all that you do, you get this value, right. Please check these numbers, I hope I have done it correct. And the critical pull up distance also we can find out, and that is from this particular expression that is given here, and here W A we will substitute 44 millijoule per meter square and all the other quantities 2 into 0.48 in the denominator 0.48 square, and this is mu here and then L square and blah blah, and finally you get that it is about 73 nanometer, okay, because it comes out to be 0.0733 micron. So, that much is the pull up load, pull up distance, critical pull up distance at which this separation occurs. So, very small actually. So, now we will go to the next problem, in which case we consider that the film at the top surface remains in perfectly slips. So, there is perfect slippage at the interface. So, we have this condition, in the previously we are considering there is no slip, but now we will have perfect slippage. So, the other extreme of this spectrum. So, in that case when they get a perfect slippage, so that means there is no shear stress that develops. Let us say x j, okay, at z is equal to h is equal to 0. So, that is the boundary condition that we need to apply over here. Earlier we were applying u is equal to 0, but over here the shear, there is no shear at this interface and so therefore we have to use this particular boundary condition. So, this dimensionless horizontal deformation we have already derived. Okay. After doing those, we considered the lubrication approximations, and that means h by l is much small, and then finally we do the integration of the stress equilibrium relations. So, stress equilibrium relations we simplified it, and then we can integrate it, and so this is the equation that we obtain after this integration. So, see over here u is equal to this. So, we will now apply the boundary conditions which are slightly different at right, we have to see that. Now, let us see that at, let us say z is equal to 0, okay, u is equal to 0. If that is the case, then see, this will give rise to c of x is equal to 0, and we have to write at z is equal to h, I was writing it x z is equal to 0. So, x z, okay, is what? So, we have to first write it in dimensionless form, remember that. So, we have to write in dimensionless form. So, if I write dimensionless form to see that which terms are important, that is all we are going to do. So, mu into del u by del z plus del w by del x. Now, if I write dimensionless quantity, so it will be mu, and then here it is L by h del capital U by del capital Z plus this is h by L del capital W by del capital X. So, I have just written in the dimensionless form and using the dimensionless quantities or characteristics quantities. So, L is the characteristic quantity in the x direction. So, for U, and h is that for z direction. So, therefore, that is all I have done. So, what we see here is this: mu will be equal to mu into this is, let us say, L by h, L over h. So, that will be equal to del u by del z plus this will be h square by L square del w by del x. So, see, this quantity is much smaller than 1 that we have defined earlier lecture, and we know that this, when you write in dimensionless form, these partial differentiations like del u by del z, del w by del x, these are of the order of 1. So, therefore, this quantity is much smaller. So, therefore, we can actually neglect, okay, these terms. So, in the shear stress, this expression we have actually, this is equal to we have 0 equal to, let us say, mu into del u by del z. So, this is the condition that needs to be used. So, we are again dimensionless form. So, let me write it dimensionless form. So, it will be actually del u by del z, that has to be equal to 0. That is the condition that needs to be used. So, here from this expression, let us therefore obtain del u by del z. So, del u by del capital Z, so that is equal to, let us say, epsilon square by 1 minus 2 sigma, this is del of A of x by del x, and this is 2 z. So, it is z here, and plus this is B of x, because Cx is already 0, we have already stated that. So, at z is equal to h, this del u by del z is equal to 0. So, that is 0 here, and this is epsilon square by 1 minus 2 sigma, and this is del of del actually dx, because A is a function of x only. So, d of x into h plus B of x. So, we get an expression for Bx over here, we will do that. So, we have already done that. So, here B of x, therefore, minus this is epsilon square 1 minus 2 sigma, and this is h square, so h actually. So, it is h by 2, not h by 2, this is after all that it is actually h, sorry, this is h, right. And so, here and del by del x, that also have to write. So, d by d of x, actually not del, d of dx. This is equal to like this, because this is, it should be d, because A is a function of x only. So, okay, like that. So, then u is equal to, therefore, will be equal to epsilon square by 1 minus 2 sigma, and let us say d of A of x by d of x, and here it will be z square by 2 minus this is z into h. So, this is the solution for u that will be obtained. Okay. And now let us say that we obtain W. For that we have to use that compressibility condition. There we have to obtain del u by del x. So, let us obtain del u by del x here anyway. So, del u by del x, so that will be equal to epsilon square by 1 minus 2 sigma, and this is d square d of x by dx square, and this is z square by 2 minus zh. And so, the expression for right, we have already obtained that. So, we have to write it like this. So, here this is the equation that we had derived earlier. So, here del w by del z, okay, so that is equal to minus of 1 by 2 into 1 minus sigma into del u by del x minus a of x. So, this is equal to minus of 1 by 2 into 1 minus sigma, and del u by del x is equal to epsilon square by 1 minus 2 sigma into del square del of x by del x square, okay, into z square by 2 minus z minus a of, so del u by del x is done, minus a of x, okay, that is the way it is. So, del w by del z is equal to minus of 2 1 minus sigma, this is fine, right, this is okay. Yeah, this is fine. So, then w we can integrate now with respect to z. So, I will get here 1 by 2 into 1 minus sigma into epsilon square by 1 minus 2 sigma here, and d square actually, right, do not write d, so d square here by dx square into, if we integrate it, so it is z cube by 3, so it is 6 here, minus z square by 2 here, and minus a of x into z plus, say this is c of x, c of x, let us say, or some quantity like that. So, here at z is equal to 0, w is equal to 0 from that. So, this is equal to 0, okay, because at z is equal to 0, this w will be equal to 0, and at z is equal to h, w is equal to delta, that is the, okay, I have taken d is equal to 0. Okay. So, at z is equal to 1, because z is equal to h means capital Z is equal to 1, that is correct, and here w is equal to delta means deformation. So, capital W is equal to delta. So, this delta here, remember delta by h, that is the thing. So, anyway, so this is w, this is equal to minus of 1 by 2 into 1 minus sigma into epsilon square by 1 minus 2 sigma, and here d square of ax by dx square, and this is z is equal to 1. So, it is 1 upon 6 minus 1 upon 2 minus this is a of x, z is equal to 1 there. So, therefore, this is equal to, this is 1 by, so this is 3 by 6, this is 3 by 6, so it is 2 by 6, so it is 1 by 6. So, this is equal to 1 by 6 into 1 minus sigma, this is epsilon square by 1 minus 2 sigma, and this is d square of a of x by d of x square, and that is equal to minus of a of x. So, it is 1 by 6, 3 by 6, minus is 2 by 6. So, 2 by 6 get cancelled. So, it is plus 1 by 6, that is okay. So, d square I by dx square, therefore, I can write, I can write in terms of a function of differential equation with respect to a of x dx square, okay. So, that is equal to, that is minus, and let us write it like this, this is 6 into 1 minus sigma into 1 minus 2 sigma by epsilon square, 6 square into a of x. This is equal to delta into same thing. So, it is 6 into 1 minus sigma into 1 minus 2 sigma by epsilon square. So, this is what I will get. Now, if you remember that we had gotten exactly same kind of equation in the earlier case also, by instead of 6 we had 24 there. So, this is the expression. So, we had 24 there, okay, and then we had solved this problem. So, we had considered, okay, we can consider here as equal to C3 and this whole thing as C4. So, C4 here 4. So, C4 divided by C3 is equal to delta here, remember that. So, we had solved this problem. Now, this equation looks exactly the way that we had solved it in the earlier case, in which there was no slip contact. In that case, I had C1 and C2, now we have C3 and C4, and we can actually solve this equation, and I will take it up, the solution of this equation, and then further expression of the load that needs to be applied in this particular case, and then finally the pull off load and all that in the next lecture. Thank you.